Okay. So welcome everyone to the third talk in our summer Chilloquium, co-organized by Harvard and MIT Society of Physics students. My name is Minchul Park. I'm an undergraduate studying physics at Harvard, and I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderators, Tung and Kwan, and we are very honored to have Professor Juan Maldacena from IAS Princeton to speak with us today. If you have questions at any time, you can raise your hand in the Zoom participant sidebar and we will call on you. Or you can privately send a message to me and I will ask for you. We will prioritize those who raise their hands in order to make our event feel as conversational as we can. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they are speaking. And also have their video on if you are willing and able. Now, before starting the talk, let us briefly introduce today's speaker, Professor Maldacena, to you. And Tung, would you please?
All right, thanks, Mincho. We are extremely excited to have Professor Juan Maldacena give a talk with us today. Professor Maldacena is the first Feinberg professor of theoretical physics at the Institute for Advanced Studies. In 1997, Professor Maldacena published a profound paper on holographic duality, which is among the most cited papers in physics. Since then, he has been studying this relationship further in order to understand the deep connection between black holes and quantum field theories. Also, he has been exploring the connection between string theory and cosmology. Thank you very much, Professor Maldacena, for giving a talk at Chilloquium this week.
Okay, it's a pleasure. Can you hear me well? Yeah, okay, great. And please, I reiterate what was said, that you're welcome to ask questions at any time. Okay, so I was asked to give you a little bit of my sort of path through physics. And so this talk will contain more personal history than most colloquial. So I'll start by saying that I'm a theoretical physicist and I work at the Institute for Advanced Study in Princeton. And I have worked on quantum gravity, quantum field theory, string theory, and various aspects of cosmology. I was born in Buenos Aires, Argentina, 54 years ago. And when I finished high school, I wondered whether to study physics or engineering. And in Argentina, you needed to decide before you enter university. My father was an engineer, so I knew what engineering was like, and I decided to do physics since I didn't know what that was like. And I started that and I liked it. So I decided to study physics at the University of Buenos Aires. This is the physics department picture. And in university in Argentina is free, and also there is no entrance exam. That means that in the first few years, everyone wants to go to the university, and it's a big chaos, quite different perhaps from the experience you might be familiar with. But well, it was interesting. And after a couple of years in the University of Buenos Aires, I went to Physics Institute. I got a fellowship to study at the specialized Physics Institute, where you could essentially study only physics. So it was not like the universities you're going to, where you have all other subjects. It was far from Buenos Aires, and these are a couple of pictures from the place. And in our last year, we had to do a research project, and I was interested in particle physics. I liked mathematics, and I liked the fact that quantum field theory involves some interesting mathematics, and that drew me initially a little bit into particle physics and quantum field theory. I was also interested in general relativity, and there was a young assistant professor who had just come to the institute, who had been a postdoc at Trieste, and when he was at Trieste, he learned about string theory. And so when he came back, he was just the only person working on string theory. And I had already a friend, an undergraduate, that was working with him on string theory. So I decided to try to do that because it would help me learn about aspects of particle physics and also aspects of gravity. So I thought it was an interesting area to start working on. So I asked Gerardo for a project, and he gave me a reasonable and doable project. It was basically a very technical calculation, but it helped me learn the basics. When I finished after a total of 6 years, I looked around to see what I could do. I guess you'll probably be in that situation when you're finishing your undergraduate. And there were various options of what my classmates and I were doing. One could work at a company or one could continue the academic career by pursuing a PhD program. And this could be done either in Argentina or abroad. So I applied for graduate schools in the US, and I was admitted to only one. And that one was Princeton University, which was really an excellent place, and it would have been my first choice. So a PhD program is a bit like being an apprentice to be a researcher. So you are learning how to do research. So in your undergraduate, you typically learn well-established physics. But when you're a graduate student, you learn to tackle new problems. And the new feature that arises then is that you don't know whether these problems have a solution or not. So it's different than working on a problem set where you know there is a solution. Here, you don't know. So I was going to Princeton, so I was going to the Center for String Theory and Particle Physics. So doing research in that area was fairly natural. Now the mood in particle physics was a bit negative because the SSE, or superconducting super collider, had just been canceled. It would have been an accelerator with 40 TeV center of mass energy. And it seemed that one would have to wait for a long time for the LHC, many years into the future. Of course, now the LHC has been on and has produced wonderful results. But at the time, that was a long time into the future. But the mood was a little bit more positive for string theory. At the time, people were working intensively in the so-called string theory compactifications. So there, the idea is that we live in 4 dimensions. Our 3 dimensions of space are large, and then there are six extra dimensions that are small and curled up into some complicated shape or space that is called it has some name, doesn't matter. But depending on the shape of those spaces, you would get different effective 4-dimensional particle physics. And so the idea was to understand whether it would be a shape that would give us the standard model of particle physics. And this search for this shape continues until today. And since then, many more possibilities for this so-called compactifications have been discovered. Now, I had a kind of strong background because I had studied physics for 6 years. And so I passed all my requirements in the first year, and I started to look for an advisor. And so I looked first for a summer project, and I talked to Curtis Callan, who gave me one that involved understanding the Ising model in 2-dimensional hyperbolic space. He gave me the project at the beginning of the summer, and then he disappeared for the summer. And I have to confess that I didn't do much progress in that particular project. But when he came back, he gave me another project involving 2-dimensional conformal field theories with the boundary. So these are 2-dimensional field theories that have a scaling symmetry. And when you put a boundary, there could be some interesting interactions at the boundary. And this was about one such problem. I really, at the time, thought it was not very interesting, but it looked doable. So I worked on it for a while and eventually found a way to solve this problem. Now, I should tell you that at the time during graduate school, I was not very motivated because I felt that I was not good enough and I would not get a very new important idea. And this is a feeling that many graduate students have. And so if you have it, don't be bogged down by it, just ignore it and go ahead and continue working. That you will get some interesting idea. Now, some of my classmates were working on black holes, and that sounded more interesting, like a more interesting area. So I told my advisor that I wanted to work on black holes, and I felt I had enough with conformal field theories with the boundary. And Ashok Sen, so another string theorist, string theory researcher, had found some interesting black hole solutions in string theory, which had some properties similar to oscillating strings. So some interesting connection between string theory and at least some black holes. And there was a new postdoc at Princeton, Amanda Pitt, who had worked on black hole solutions as a graduate student. So my advisor, Amanda, and myself worked on some of these black hole solutions. And so we found some oscillating string solutions for some supersymmetric situations. So those were some strings where the strings were wrapped in some internal dimension and they were oscillating in some simple way. And so we could find the corresponding gravity solutions. Now, about that time, so that was maybe 94, 90, 95, there were a number of new and interesting results in string theory. It was a period that people called the second superstring revolution. And I followed these results, but did not work actively on them. But then there was a very important discovery by Joe Polchinski, which was part of these results. He had found some new objects in string theory called D-branes. So a D-brane was a kind of soliton that the theory has. It could have various dimensionalities. It could have 0 dimensions, so it would be like a particle. It could have 1 dimension, it would be like a string. It could have 2 spatial dimensions, it would be like a membrane. And they had a very simple technical description in string theory. They were described as objects where open strings could end. So you could have open strings that were ending on these objects. And by considering the properties of this and their interactions, you could describe the physics of these objects. And it was great because I knew precisely the mathematical background to deal with them. All thanks to this previous work on conformal field theories with a boundary, which was the problem that I thought was uninteresting, but it was a problem that proved very useful in this case. And the connection is that when you think about a string, so a string is a 1-dimensional object, but when it moves in 2 dimensions, it describes when it moves in 10 dimensions or in the space where it moves, its word volume describes a 2-dimensional surface in the same way that a particle moves, as it moves in space-time, this describes a line in space-time, 2-dimensional, the string describes a 2-dimensional surface. And if it is ending on a D-brane like this 2-dimensional surface has a boundary. And so I was set to work on this, and this was a new tool, and these D-branes were a new tool that could be used to analyze many problems that were previously intractable within string theory. So some of us immediately tried to see how one could use them to describe black holes. At the time, an important problem was to understand the entropy of black holes. It continues to be an interesting problem, and important. So let me give you a little background on. So now I'm going to describe for you a little bit of a background of this problem of black hole entropy. So black holes are not perfectly black once you take into account quantum effects. So this is a famous phenomenon that was discovered by Hawking in the 70s. And so Hawking found that a black hole has a temperature which is inversely proportional to its size, to its radius. So the radius of a black hole is given in terms of the mass by this formula. And here is the temperature in units where h bar c and the Boltzmann constant is 1. What this formula is saying is that the typical wavelength of a Hawking quantum will have the typical Hawking quantum emitted at temperature T would have energy T and will have wavelength which is of the order of the size of the black hole. Okay. Now this is a very tiny effect for big black holes. So big black holes are the ones that are produced by astrophysical processes. So for astrophysical black holes, this temperature is very, very tiny. And this is not an effect that has been seen or certainly has not been seen for astrophysical black holes, and probably will not be seen for astrophysical black holes in the foreseeable future. I should mention in passing that there is a similar phenomenon in cosmology that is responsible for the generation of the primordial fluctuations, cosmological fluctuations. So there is a related and similar phenomenon in cosmology that indeed form parts of the standard picture for inflationary cosmology. Now, an interesting thing about this effect is so surprising that the black hole can be white. So imagine that, so we could ask, well, one question I could ask you is, how big should a black hole be so that it will look white to our eyes, right? So you can think about this question for a little while, and if you want to interrupt me, maybe you can tell me what the answer is. So in order to figure out how big it should be, we should first figure out well, what the wavelength of, so it should be the size of the wavelength of white light, right? And so that's the light we see from the sun. So the temperature should be of order the temperature associated to the surface of the sun. And the size will have to be of the order of the wavelength of the light. So that's you know, less than a micrometer, half a micrometer or so. So roughly the size of a bacterium. So a black hole like that would look white to our eyes. You could also ask what is its mass. So you can figure out the mass from the formula we had before, relating the radius to the Newton constant and the mass. And that gives you a mass which is around the mass of a continent. So it's a pretty heavy object. And one question, another question you can ask is whether it does emit enough radiation for us to see it. So notice that the black hole that would emit white light would be very, very small, the size of a bacterium. So the total amount of light that is emitting is not very large. So it's not like looking at the sun, it's looking like a little tiny dot that is emitting light. And so you can figure out, you can calculate whether your eyes would be sensitive to it. And they will be sensitive, so you can figure out what, if you want to do this exercise, you can figure out, well, go and look up what the sensitivity of our eyes is, and then see whether you could actually see it. And actually, there is an interesting twist to this problem, which is that if you get very close to this black hole, you might be killed by the tidal forces. So if you're very close to this black hole, maybe you are orbiting this black hole, then the tidal forces would be pretty big and they might kill you. So you actually have to be far enough from this black hole for you to be able not so that you're not killed by the tidal forces. Okay, so those are some fun questions one could think about. But well, so this was just a fun thing to think about. This temperature of the black hole, as we said, is not important for astrophysical black holes, but it leads to interesting conceptual questions relating to black holes. The first one is that, well, a black hole looks like a single gravity solution, but nevertheless, it looks, because it has this temperature, it looks more like a thermodynamic object. So some object that has maybe many internal degrees of freedom, and it's at some finite temperature. In fact, you can use the first law of thermodynamics that says that the change in entropy is equal to the change in the internal energy, in this case, the mass of the black hole, divided by the temperature. And so the Hawking formula gives us the temperature as a function of the mass, or the Schwarzschild radius. And so we can integrate this equation and find the entropy. And then we find this formula saying that the entropy is equal to the area of the black hole horizon. So the black hole is some space-time that has somehow two regions. One region can send signals to the outside, and another region cannot send signals to the outside, and they're divided by a surface called the horizon. The surface is not something you can locally measure. It's some sort of dividing line that separates two regions of space-time. And if you calculate the area of this horizon, is of order, the area is 4 pi a sphere times the radius of the horizon. So that's given by this formula we used before. So in units of the so-called Planck scale, so here I've set again h bar and c and k Boltzmann, etc. to 1. And so this Planck scale is a length scale that you can form out of the gravitational constant and h bar and the speed of light, that works out to be a very short distance of order 10 to the minus 33 centimeters. And so given that this distance is so small, that's the fact that this distance is very small is related to the weakness of gravity. So the fact that G Newton is so small. And that means that a black hole that is somewhat macroscopic, so that has a relatively large size in Planck units, will have a very big entropy. Okay, so so this is an entropy that we computed just purely using the first law of thermodynamics, and is similar to an entropy that an experimentalist could measure if he or she measures takes some material and then heats it up and sees how much energy is thrown into the material and at what temperatures. Then using this, that experimentalist can compute the entropy, sometimes called the thermodynamic or microscopic computation of the entropy. But since the time of Boltzmann, we think that entropy should also be equal to the logarithm of the dimension of the Hilbert space accessible to the states of the system, or to the system, or in other words, equal to the log of the number of states that have that energy or are within some energy band. So the question is whether for the black hole, this is also true. So this is true for all systems of ordinary matter. We find it always very useful to think of entropy in this way. This is the way we understand entropy of an ideal gas, for example, and of any other material that we normally encounter in the lab. And so is this true also for black holes, and what are those states? Now, this is the question, and at the time we were trying to find this number of states by thinking about some configuration of these strings and d-branes. So d-branes were useful because they were kind of rather heavy and where they were on the verge of becoming black holes, roughly. And so by putting many of these d-branes together, they could be arranged in various ways. And if you could count in how many ways they could be arranged, you could perhaps find that that's equal to the area of the horizon corresponding black hole. And part of the idea was also to use the extra dimensions of string theory. So as I mentioned before, in string theory, there are some large dimensions. Let's say there are 3 large dimensions. And then there could be some internal dimensions. In the simplest case, you could think of the internal dimensions as being some kind of circle. And then you could have branes that are wrapped on those circles, and they could be oscillating, carrying, let's say, momentum along one of the directions of the circle. And if you had such a situation, then from the point of view of the 4-dimensional physics, this momentum along the internal dimension would look like a kind of electric charge, one type of electric charge that the black hole would have. Then these branes that are wrapping the internal dimensions would be another kind of electric charge. So these would be theories, and they would not be like the standard model, it would be other theories where we would have different kinds of electric type charges. And so there are the so-called extremal black holes, so if you have a charged black hole, let me take a step back. So if you have a charged black hole, its mass should be bigger than the charge in certain appropriate units in order not to have a singularity. So all black holes, all charged black holes, good black holes, have mass which is bigger than the charge. And this picture that was, well, in the case, when the mass is exactly equal to the charge, we call those black holes extremal. And for those black holes, Strominger and Baffa managed to actually reproduce the entropy of black holes using these ideas. This method works very well and reproduces the entropy for, well, in many cases. And then, so after that paper came out, we found we wrote some other paper where we tried to understand the near extremal case, so trying to find a small modification of what they actually had done in order to take into account situations where the mass was slightly bigger than the charge. And so in their situation, they had roughly a configuration of branes that were wrapping the internal dimensions with momentum moving along one direction, purely along one direction. And we had the idea of perhaps just including momentum moving in the opposite direction, a little bit, but a small amount. And in this way, one could find an entropy which would match the entropy of the black hole. And the match worked well in some cases and not so well in some other cases. So I worked on various aspects of this story during the last year of my graduate school years. I had applied previous to that to postdocs, and I had gotten a postdoc at Rutgers University, which had an outstanding string group at the time. Now I should mention just as a general background, what the typical career of someone who's doing research in at least theoretical physics, or many times just in physics in general. You typically would finish your PhD, and then if you want to continue the academic career, you would do perhaps one postdoc, which a postdoc is a research job where you do research for 2 or 3 years. And then maybe you do a second postdoc, another research job. And then during this time, you write papers, you do research on some new area of physics, and so on. And then eventually you'll find, you apply for a faculty position, and then you might get your first faculty job. And then you'll continue getting longer and longer term jobs. Maybe eventually you might get tenure, and all these faculty jobs involve both teaching and research, while the postdocs are just purely doing research. Now, some people also find jobs outside academia. So at any time you can switch and decide to work. You say, well, I don't like academia anymore, and you can go and work on private companies. And I had students that went to work in Google doing artificial intelligence, and they worked in banks or consulting, etc. And of course, I also have many students that continue the academic career and are professors at various places. Now, in my particular case, this work we're doing on black holes got people interested, and I started getting some faculty offers. So in the end, I went to Harvard University. Andy Strominger, those of you who are at Harvard, maybe you know him. He had just moved to Harvard, and he convinced the department to hire me. And I had written several papers with Andy, and he was really a very good mentor that helped me start as a junior faculty while I was there. Now, during my stay at Harvard, I wrote this paper that was mentioned on ADS-CFT, or sometimes called gauge gravity duality or holography. And this was basically a continuation of this work on black holes. Several researchers were doing computations with D-branes and compared them to black holes. I mentioned one of them. And sometimes these computations agreed, and sometimes they didn't agree. And so it wasn't completely clear what the precise connection was between the two things. And so the duality was a precise statement for the connection between the two. And so let me roughly tell you what it is. And before I tell you, we need to discuss a bit of space-time that is called anti-de Sitter space. So anti-de Sitter space is the simplest solution of Einstein's equation with negative cosmological constant. So space, just a space with no time, with constant negative curvature, is a two-dimensional hyperbolic space. And we've already seen a picture. This is a picture of hyperbolic space. So here, each of these fish is supposed to have the same proper size. And the size of the fish is becoming smaller as you get close to the boundary because of the effect of the projection from the negatively curved space to the flat surface on the screen. So similar to the distortion that happens when you project the surface of the sphere to the plane to make a world map. So this is just a hyperbolic space, a space with constant negative curvature, and the simplest curved space introduced by Lobachevsky. Now, it's called anti-de Sitter because de Sitter was an astronomer who introduced another space, which is a solution with positive cosmological constant that describes an accelerating, expanding universe. So our universe is closer to de Sitter than to anti-de Sitter, and in fact, it would be nicer to have a similar relationship, including de Sitter, but the one that is best understood is the one that involves anti-de Sitter. So in some sense, you could say we made a sign mistake. The one that is most interesting is the case of de Sitter, but we have to the case where we can say something about is the case of anti-de Sitter, which has the opposite sign for the cosmological constant, and it does not have that, it's not as similar to our universe as the case of de Sitter. But anyway, let me say a little more about how anti-de Sitter space looks like. So you can think of anti-de Sitter space as having spatial slices, which look like hyperbolic space, like this one. And then there is also an additional time direction. And so a stack of these hyperbolic disks. also the time direction kind of stretches as you go near the boundary. That means there is a gravitational potential that pushes you to the center of this hyperboloids. So in some sense, the de space looks a bit like a gravitational box or gravitational cylinder where everything sort of gets pushed towards basically the center of the cylinder and repelled from the walls of the cylinder. Now, this is just a projection of that four-dimensional space into a finite region of of the screen in this case. But this boundary is really infinitely far away if you follow a geodesic or a straight line at a given moment in time. So it takes infinite spatial distance to the boundary. However, if you send a light ray can go to the boundary and back in some finite time. So that's because this time direction also gets stretched as you approach the boundary. So this surface that is very far away is what we are calling the boundary, and will play an important role in a second. So this ADS, CFT, or holography connection is a conjecture that relates the gravitational physics in this type of spacetimes. By gravitational physics, we mean, well, anything that gravitational that can go on in the interior. We can have gravity waves, matter, etc., interacting with gravity in the interior. And that's all of that is supposed to be described by a boundary theory. So a theory that lives purely on the boundary, purely here in this blue region. And the theory of the boundary is a theory that contains just strongly interacting particles, but without gravity. And so this is a conjecture, so we don't know for sure. It's not a mathematical theorem. It's a conjecture that there is a lot of evidence that the conjecture is right. So at the time that this was proposed, there was not so much evidence, but over the about 25 years from then, there was a lot of more evidence that was found for this relationship. Now, this is a kind of picture that tries to explain what I was saying before. So in the interior, you could have some particle that is moving, held by the gravitational potential that does not let it go near the boundary. And here on the boundary, we see strongly interacting particles. So this funny motion here tries to represent the particles that are strongly interacting. And in order to have a good gravity description in the interior, we need a large number of strongly interacting particles on the boundary. Now, you can ask what a black hole would be in this type of description. So in principle, we could describe either this anti-de Sitter space with a few particles, and we could have a large number of particles in the interior that collapse and form a black hole. So the idea is that if you form a black hole, so a black hole should correspond to a large number of particles moving on the boundary. It should look more like a fluid. In this case, this is a bit like a rotating black hole. It's moving around. I really got tired of making this little pink particles, but it should be more like a fluid on the boundary of a large number of strongly interacting particles. And then the idea is that the temperature and entropy of the black hole come from the various states. So they come from the motion of these particles, essentially. In particular, the entropy comes from the number of configurations available for this particle at a given energy. So the statistical description of these black holes is given in terms of these particles that live at the boundary. Now, this was again used by many people to produce further and new interesting results. And I basically continue to study aspects of this and related topics. I mean, one topic that I was studying recently is the connection between wormholes and entangled states. And I'll probably briefly discuss this now. So what is a wormhole? So a wormhole is a kind of connection between two distant space-time points. And it arises from the simplest solution of general relativity, which is the Schwarzschild solution. So let me just describe a little bit for you the Schwarzschild solution. This is not how Schwarzschild thought about it. This is an understanding that developed over the years after people understood the proper interpretation of the full extension of the Traversable solution. Now, this solution is a four-dimensional space-time, but is rotationally invariant. So when we describe it, we will suppress the directions of the sphere. So at each point in this two-dimensional picture, there will be a sphere, and these two dimensions that appear here are roughly the time direction and the radial direction, going roughly horizontally. Now, this is a kind of map of these two-dimensional sections. Sorry, I should say that at each point on this space, there is a two-dimensional sphere. This part of the space-time represents slices of the space-time that include the time and radial directions, and they've been sort of deformed in such a way as to fit in this finite region of the plane. So in particular, the radial direction could go all the way to infinity, and infinity corresponds to this black line far away. So that's the region infinitely far away. So for example, if we take this blue slice far away will look like a three-dimensional space, flat space far away. As we go deeper in, the size of the two-dimensional sphere shrinks to a minimum that corresponds to this region here in the middle. And then as you go to the other side, we have again some three-dimensional space. So that's the geometry of this slice. Now, I said before that the time and radial direction were deformed, but they were deformed in such a way that light rays travel at 45 degrees in this diagram. So and that's a useful notion because if you want to send the signal from this point to infinity, the fastest way the signal could go is just to move at 45 degrees. Okay. In particular, if you want to send a signal from this point to infinity, you cannot, because from this point, the fastest you can move is just by moving outwards, and you will hit the singularity before you get to infinity. So this type of diagrams, sometimes also called Penrose diagrams, are a useful representation of the space-time and their causal features. So from this space-time, you see that there is this region that can send signals to infinity and can receive signals from infinity. And this region here is called the right exterior of the black hole. So it's the exterior of one of the black holes. It looks like the exterior of a black hole. Sometimes this future region is called black hole, and this past region is called white hole. This is not related to the white holes we were talking about that will look white to our eyes. This is just the name for this particular past horizon. Okay, and so the picture contains two black holes. So there's a second left exterior, which is similar, and they are connected by this wormhole. Now, this is purely a vacuum solution of the vacuum Einstein equations, and there is no exotic matter supporting this wormhole. It has two exteriors, and they are sharing an interior. So notice this region that is behind both of the black hole horizons. It's what we normally call the interior of the black hole, and it's shared between the two sides. Now, this surface here is sometimes called the Einstein-Rosen bridge because they were the first to understand that the Schwarzschild solution described two black holes connected in this way. But this bridge is time dependent. So if you evolve in time, so at a later time, you'll have another slice here, so another three-dimensional slice. And it would not look like this one. It would look more like this one in the sense that this region connecting the two horizons will get longer and thinner. So we'll get thinner here. And in fact, the radius of the two sphere has some size here, which was the size we had here. It gets smaller when we get to this point here. And at this position here in the diagram, the surface of the two sphere shrinks to 0. And that's a place where we'll find the curvature singularity. And as we approach this singularity, the tidal forces also become infinite. And so anyone who is falling into a singularity will die. Okay, so it's not good to get into this region of the black hole. But what I wanted to emphasize here is that these wormholes are not wormholes that stay on forever. They exist at this time, and then they stretch and collapse. Okay, and someone who would try to travel from the left side to the right side, the fastest that person could go is just to move at the speed of light. And so that person would move along at the speed of light, will see the wormhole stretching, the horizon moving out, and eventually it is also shrinking, so it will collapse before that observer can cross to the other side. So these are not traversable. So in fact, there is a very similar solution. So in this particular solution, the Schwarzschild solution, these two black holes are in two separate universes. We have two separate universes, and each of which has a black hole, and there's a wormhole connecting them. Now we could put these two black holes in the same universe. That's not exactly the same solution, but it's pretty close. It's also close to the horizons of each of the black holes. It will look like the Schwarzschild solution. So in this case, we have two black holes. They are joined by a wormhole, but these are wormholes that used to send signals. In particular, they will not lead to any faster than light propagation or no violation, and they are not traversable. Now, what are we to make of this geometry? So one option is to just ignore them. In fact, the formation mechanism. So if we had in nature, let's say, two separately collapsing black holes, then usually there is matter inside, and the geometry would not be of this form. So the in the interior that will change the form of the equations so that the black hole will have a single interior. So each of the black holes has a single interior. So in fact, if you observe two black holes in nature, they will not be joined by this type of wormhole because they were produced by gravitational collapse. And so each black hole is supposed to have its own interior. So that's one option, to ignore them, and that's what most people did. But you could also try to understand them better. So they are simple solutions of Einstein equations, and we'll come back to them. Well, we'll come back to them actually now. So in fact, there is an interesting interpretation of these geometries, which is as follows. So we saw before that each black hole can be viewed as some kind of quantum system having a finite number of degrees of freedom or Hilbert space, given by the exponential of the number is given by the exponential of the entropy or the area of the black hole. And then one could take identical quantum systems and one could entangle them. And we could entangle them in a very special state, sometimes called the thermofield double. So this is, so if you have some system, so if you have a quantum system that has a sequence of energy levels, you could then entangle it with an identical system that has similar, well, the same energy levels, and you can form this pure state out of the system. Now, this state had been considered before because it's if two systems in this state and you only look at the right side, then you will get a density matrix, which would be the thermal density matrix purely from the right black hole. So this is this can be done for any quantum system, for a harmonic oscillator, for a spin 2 system, for a spin 1/2 system, for any system you could do this. You only need to know the energy levels of the system, and you can construct this state. Okay, so if you have these systems, then you can consider them entangled in this way. And the idea is that if you consider them entangled in this way, so any of these systems are the energy levels corresponding to a black hole, geometry that has a wormhole connecting the two sides. And we call this ER equal to EPR because Einstein and Rosen were the ones who found the wormhole connection between two black holes, and Einstein was the ones who highlighted the entanglement when you have two separate quantum systems. Now,
Professor,
the story I like.
excuse me, Professor.
Please, yeah.
Oh, sorry. Oh, yeah. I just want to like ask about whether we can like open up the Q&A session in like after 10 minutes, if possible.
Sure, yeah, I can.
Yeah, thank you so much.
Then
Thank you so
relatively
much.
quickly. Or if people want to ask questions now, I'm happy to entertain
Oh, I
questions
see.
now.
I see. I think there are no question on the sidebar or like any popped up questions. So yeah, we can wait after 10 minutes to take some more questions in the Q&A session.
Okay, wonderful. Yeah.
Thank you so much.
Sure, yeah. So there's a story I like to tell to explain the funny feature of this geometry, and this involves the following situation. So there were two people. So one called, let's call him Romeo, called her Juliet, and they liked each other, but their families wanted to keep them apart. But they were physicists, and they were very smart, and they read about wormholes and entangled states and so on. And so they had very powerful quantum computers that could be used. They exchanged entangled qubit pairs, and from these qubit pairs, they made two entangled black holes. And then after they did that, they each jumped into their respective black holes. Okay. And when their family saw this, they thought they committed suicide. And also the person telling the story also wrote that. However, however, because of the wormhole that was created, even though Romeo and Juliet each fell into their own respective black holes, they could actually meet in the interior. Okay, so they met in the interior, and in this version of the story, they just die in the singularity of the black hole. Okay, so it doesn't have such a good ending, at least for now. But you could wonder whether there is a better way to do things. And in fact, there is an interesting way to make these black holes traversable. And so we'll discuss that in a second. And this is something that was done by Gao, Jafferis, and Wall. Daniel Jafferis is a professor at Harvard that maybe you might have met him. And Ping Gao was recently a postdoc at MIT and was a student at Harvard also. Okay, so I'm going to discuss how these wormholes can be rendered traversables and how that's related to quantum teleportation. So let me say a few words about quantum teleportation, if you haven't seen it. So it's basically the following idea. So Charlie wants to, so there is Bob and Alice, the proverbial two people of the quantum information literature. And Charlie gives a qubit to Bob, and Bob has to send it to Alice. Now, the trick is that if Bob and Alice shared an entangled qubit pair, then Bob can send this qubit to Alice by just sending classical information. In principle, sending a qubit is much harder than sending classical information. You have to, naively would say, you have to physically transport the qubit. Here also, you have to physically transport a qubit, not the original, this qubit that was sent, not the message, but you have to transport one to really create this entangled, in order to have this entangled qubit pair. But once you have this pair, then you can use a certain protocol to send the qubit. So the idea is that Charlie gives the qubit to Bob, and then Bob does a complicated joint measurement on Charlie's qubit and this member of the pair. And then there will be, now these are two qubits, so the protocol will give two classical bits as an answer. And then Bob sends this classical information to Alice. And then Alice does an operation on this on her qubit that will produce here the message, the original qubit that Charlie had sent. Now, one question you could ask is whether you would like to be teleported. So imagine you build a giant teleportation machine with many qubits. And instead of Charlie's qubit, it's just you that you're going to be teleported. And the problem here is that this measurement is a measurement that mixes all these qubits with these ones. So this is like putting you in some kind of blender that shreds you to pieces and mixes them very well with these entangled qubits. And then you do a certain measurement, and then you send the classical information. Now you're guaranteed that here you will be restored and be built again, but this experience of being shredded to pieces looks not very fun. Now let's return briefly to our story of Juliet and Romeo. So Juliet tries to convince Romeo to build a giant teleportation machine and suggests that he teleports himself. But Romeo, for the reason I just explained, is worried about the process. But Juliet then suggests using these entangled black holes. So how would the teleportation look like in this case? Well, we would have Bob's, the black hole on one side and Alice's black hole on the other, right? So we have the two black holes. And remember, in this setup, they created these two black holes in a precisely entangled state. And then the idea is that Romeo jumps in, that's the green arrow here. And then after a while, there is a machine here that measures the Hawking radiation coming out of this black hole and sends the answer to the black hole on the right side. And then Alice on this side, operating on this black hole, can send the negative energy pulse into the black hole. She can do this because these degrees of freedom are entangled with each other. And by knowing the results of these measurements, she can do an operation that actually will extract energy from the black hole. And so this energy, when you send some negative energy pulse, so if you send positive energy, it usually implies there is a time delay, so this signal will emerge a little later. But if you send negative energy, you could come out earlier, and in that way can extract the signal out of the black hole. So this is a situation similar to what we had in teleportation. So the entangled pairs here will be all the black hole degrees of freedom that are entangled between the left and right. The complicated mixing operation is just the falling into the black hole. And the extraction procedure is this procedure that Alice does here to send the negative energy pulse. But the interesting aspect about this is that the signal that went through the black hole doesn't feel anything special when, so let's say this is Romeo that is falling in here. He doesn't feel anything special when he's going through this process. And if this negative energy pulse is perfectly spherically symmetric, then he will not even feel anything special when he's extracted. So Romeo jumps in and meets Juliet, and he reports he didn't feel anything strange in the process. It was like traveling through empty space. So I guess I've given you a little flavor of some of the things we are discussing, and as some conclusions for the whole talk, let me just mention that quantum mechanics and black holes give rise to interesting questions, and they are providing an interesting perspective on the nature of space-time in the quantum theory. And this exploration really is continuing, and there are many unanswered questions. Okay, thank you.
So thank you so much, Professor Maldacena, for the amazing talk. So now we are moving on to the Q&A session between the speaker and the audience. So as Michelle explained in the beginning of today's event, please raise your hand in the Zoom participant sidebar, and we will call on you, or you can privately send a message to me and I'll answer you. And because we want to make the Chilloquium not like more conversational, we would prefer the ones who raise their hand. And now we already see 3 participants who raise their hand. So yeah, let's start with Benjamin. Let's have Ben.
Yeah. Thank you so much for the talk. It was super interesting. I had a question about the last thing we were discussing about Romeo jumping into a black hole. I was a bit confused how it was possible that he could be extracted, considering that he jumped into a black hole and you can't get out of a black hole. So could you maybe say a few more words about that?
Yeah, that's a very good question. So so if you have these entangled black holes, then you can be extracted. So that's part of the interesting aspect of this story. So it's not true that you can never be extracted. So if you fall into, well, even if you fall into an ordinary black hole, in principle you could be extracted, but it's very impractical. What you would have to do is run time backwards. So you have to find a way to. So that's not possible to do in principle. But in this setup, you can in principle extract the person. But something that I did not explain is how you would make the entangled black hole pair. That is very, very difficult to do. So it's very complicated.
Okay, so Ben, do you have any further questions? Okay, so let's move on to Juan.
Hi, Professor Maldacena. Thank you for the talk. I had a more kind of general question. So just right now, I'm going to my last year, as I'm sure many other people are. And, for doing theoretical physics, in these kind of areas and that kind of thing, I was just wondering if you had any advice, when it comes to searching out for advisors or graduate schools and programs and that kind of thing that you could give. Yeah.
Well, I think it's good to go to a place where, there is a good group in, the main thing is you shouldn't narrow yourself too much in what you plan to do. So you should go to a place where you have various options. You can work, in string theory or particle physics or cosmology or various aspects, perhaps, of theoretical physics. And as you start graduate school, you look around and see what people are doing, what excites you, and in the place that you're going, maybe you find some very exciting, person that is doing something very interesting, then you would try to work with that person. Yeah, I think the beginning of graduate school is a good place, good time to decide to, what you are going to do. And you have time to perhaps go to talks and seminars in the various areas, because you might think, oh, maybe I'm interested in doing the string theory, but then once you start going to the talks and say, well, no, this is too technical or too mathematical, you don't like that, then you find something else to do. So that could happen or not. Maybe you're interested in doing particle physics and so, oh, no, I want to do string theory. But yeah, it's a good time to do that searching. Don't try to jump in and, well, you have to start immediately and so on. You just take your time and look around.
Oh, thank you so much. Actually, Professor, I think there are 4 more questions. May I ask whether they can all go over their questions, if you don't mind, or?
Yeah, go ahead.
Oh, thank you so much. So in the case next, Alex, would you please? Oh, sorry. Yeah, would you please?
Hi, Professor Maldacena. Thanks for the great talk. I had 2 things that I wanted to ask. First, on the very previous slide, you were talking about negative energy. Is that from what we hope to harness from the Casimir effect? Is that kind of the type of negative energy?
Yes.
Okay.
It's closely related to the energy of the Casimir effect.
Great. And
the Casimir effect. Yeah, let me try to explain why. So the Casimir effect, a simple situation where you have Casimir energy is when you have a circle. So you have fields living on a circle, then you will have a Casimir energy. Normally, people talk about 2 parallel plates. So that would be an interval. But also when you have a circle, you have such a thing. But here in this situation where you have the 2 black holes, you have in some sense a circle, which is a line that goes through the wormhole and then comes back out in the ambient space. And this forms a kind of circle.
Yeah, kind of like the pressure difference created by the virtual particles. Yeah.
Yes. So the descending of the classical information is what makes really this possible. So really to have a precise correspondence to the Casimir effect, you would need to establish a continuous connection between the 2 black holes. So let's say bring the 2 black holes close enough so that they can exchange particles. And that situation is literally like the Casimir effect.
And also, I know in the work that you did at the cool horizons for entangled black holes that we're discussing the ER equals EPR paper. Yeah. I think Alice and Bob's, or in this case, Romeo and Juliet's quantum computer uses local and unitary gates. I'm just curious, you can introduce non-local things like measurement and then do error correction. But what about non-unitary was the measurement. What about non-local gates? like how does this play into, like, I don't know, quantum
Well, in
computing?
principle, you can consider anything that could be reasonably realized, right? So if you want to act with gates that act on both black holes at the same time and they're very distant, you're not going to be able to realize it within an ambient space-time that obeys standard causality. But if the black holes are, let's say, close enough to each other, then you could imagine having gates that act on the degrees of freedom of both black holes. That would be non-local in that sense.
Yeah, and I guess that comes back to the question of like the creation of like the two black holes, and like how do you achieve the like topological order so that you have the two black holes there.
Yeah, that's right. So that we can only understand in very, very specific artificial systems. I wouldn't know how to do it in 4 dimensions in the standard model, for example.
Great, thank you so much.
Thank you, Rosa, and nice dog pizza.
Hi, hello. I really enjoyed the talk, and thank you for the talk. I want to ask you first. It was really interesting to hear your story from graduate studies and postdoc studies, but at Harvard. But I want to ask you, how do you like how do you learn? How do you first choose your research topic? Like, do you, for example, you said that your advisor gave you
Right.
confirmed
Well,
field theory project.
yeah.
but-
So yeah, that's right. So I mentioned that my first projects were given by my advisor. And
Yeah.
that's when you are starting, you'll get the projects from your advisor. He tells you somehow, go, let's say, in this direction. And then as you start learning more, going to seminars and you start getting more experience, you can start having, you can start seeing what questions people ask, and you can start asking some of these questions yourself. Yeah, in the very beginning, it looks like a very vast thing that, well, what am I going to do? But you will have some guidance in, this period of PhD is like being an apprentice where you're learning how to ask these questions. And typically there will be a community of, even when you're older, there will be a community of researchers, and typically people ask questions within a certain area, and there are some questions people find interesting, try to answer. And usually there are many questions that are obvious for everyone that would be nice to answer, but they are not possible to answer. So many times the trick is to find a simpler version of such questions, or something that you can actually answer. So you're always in this fine line between what's trivial to answer but not interesting, and the pieces that are interesting to answer but impossible to actually answer them. So you're in this very small boundary between the two. Yeah.
Regarding to that, I also want to ask, like, so when you have interesting questions, but like, for example, I'm relatively young and like I have some questions, but like I feel like I have to learn so much math, for example, and I feel like I don't have to learn everything, but I don't even know what I'm going to use in future, like what will be useful.
Right.
Did you ever have issues?
Right.
Like
So
that?
I think if you're interested in physics, usually you will work on some problem and you will learn the math associated to that problem. And then it will be easier because you will know which math you need to learn, and you will only learn the pieces that are relevant to that problem. And then after you work on a few problems, you will have more and more mathematical background. It's harder to just say, oh, I'm going to learn something in math. I mean, when I was an undergraduate, I did some math courses, and I think these math courses, well, maybe they taught me some math, but it was not the math that they eventually used in physics. I think you will learn the math as you are learning in physics. Theoretical physics, I mean, it's really kind of applied math, right? And so a lot of the day-to-day work of a theoretical physicist is solving certain mathematical problems. I mean, that's part of it. I mean, another part is to connect them to nature, do some interesting questions. But yeah, so you'll be learning it as you go along.
Yeah, thank you. Thank you very much.
So thank you. Next, let's go with Roy.
Thank you very much. Hi. My question was, how do you approach, I guess, your labor as a physicist in terms of like maybe your work ethic? Like how do you see, like, do you just work whenever you feel like it you want, or is it like you have to be disciplined? Like, what are the traits, or yeah, how would you describe your work ethic?
Well,
Or
I think
have
you
you
have, you do have to be disciplined. I mean, sometimes, so if you try to solve a problem, you have to be persistent. And, you know, if you try to solve a problem and the first time a difficulty comes in, you kind of switch to something else, or you do something else, then it's hard to make progress. So you have to be reasonably obsessive and reasonably persistent to try to, to solving the problem. But sometimes you have to give up. So sometimes you try to solve something for a long time and you can solve it, you have to give up and do something else. But persistence and some discipline is important.
and is it like, are you in general in like your daily life, is physics everything you do, or how do you balance, I guess, like the rest of your life with being a physicist?
Well, I think well, I more or less go to my office about, well, I go to the office for about 10 hours a day. And the rest is, well, for my family or for other things. So, but I, try to concentrate during those hours that I'm in the office. That involves reading papers, going to talks, and doing some calculations, etc.
Okay.
During the week, yeah, and I have the weekends also for my family.
Thank you.
Thank you. So, and because of the time constraint, we will only accommodate one more question from Ricky. So sorry to Dari and Kevin.
Thank you so much for the talk. So I was just wondering whether you have any advice regarding creativity, like how can we, especially in the realm of theoretical physics, how do we like come up with creative ideas, or like when we maybe how do we come up with some problems, or when we are like solving some problems, how do we come up with like ideas? Do you have any experience or advice?
Well, I think the skills are not, I think, too different from when you try to solve a problem set, right? During your undergraduate career, you had to solve problem sets. One difference is you don't know whether the problem is solvable, but you come up with tricks. One difference is that you can ask other people. So when you're given a problem set, usually they tell you think about yourself. When you're doing research, it's perfectly fine to ask other people. And sometimes you can get help from other people. But yeah, so you have to try to, try to understand the big picture, look at the problem from different angles, using different techniques, look at related problems, simplified versions of the problem. I mean, building an intuition just by doing those things.
So if that is all, thank you so much, Professor, for answering the questions.
Thank you all for listening, and best wishes to all of you.
So I have a few concluding remarks. So for those of us who are joining us for the first time today, please sign up to our Chilloquium mailing list through the link that Minchio posted in the talk. We send out a weekly email about the upcoming Chilloquium talk and a reminder on the day of the event. So if you want to stay up to date on what talks are coming up next in the summer, please join the list. So thank you so much again, Professor Maldacena, for the wonderful talk. And we'll see everyone at the July's Chilloquium events as well. Thank you.
Okay, great. Yeah, see you. Bye-bye.